to invite Mr. Anoop Kumar Pandey on stage to present his paper. Title of the paper is Quantum Communication Applications Beyond QKD.
Okay, so my paper was basically a tutorial paper, and well, I have explained many kind of quantum application beyond QKD. So usually for quantum, everybody thinks that QKD is the only thing, but there are many applications which can be performed using quantum computer. So I will take one example of blind quantum computing, where we will be using quantum application. So let me start with basic. So we already know that bits are binary digit which can exist in either 0 or 1. Now, if I talk about qubit, which are quantum bits, they can exist in a superposition of 0 and 1. And we tell this as ket psi equal to A ket 0 plus ket B ket 1. So that notation is called ket. It's called a Dirac notation. And so it is in a superposition of 0 plus 1. The coefficients A and B, they can be complex number. And since a complex number can take any infinite value, this state also can be, so this qubit also can exist in infinite states. Now, now we'll talk about some operators that can work on any quantum qubits. Now, usually in classical computers, if you remember, there are gates, like AND gate is there, NOT gate is there. So similarly, here also we have some operator which will change the state of a qubit from one to another. So for example, there is identity operator. So identity operator means it will do nothing. If it is ket 0, it will remain ket 0. If ket 1, then it will remain ket 1. Similarly, there is a X, which is a bit flip operator, and it will basically change it, similar to our NOT gate in classical computer. So 0 will be changed to 1, 1 will be changed to 0. There is one Y gate, which is both bit and phase flip. There is a gate Z, which is only phase flip. So the first 0 will remain unchanged, but the second one will become -1. Now, this qubit state, we can also represent using matrix. So how do I represent? So we can represent it using a column vector. If you remember, A and B were the coefficients. So that A and B I can write as a column vector. And 0 I can write as 1 and 0. 1 I can write as 0 and 1. So in that way, I can say that finally my ket psi is a combination of A ket 0 plus B ket 1. So it's simple matrix representation. One operation on this qubit is called adjoint operation. Adjoint operation is basically transpose and take a conjugate, complex conjugate. So if you see, column vector was there AB. When I transposed, it became a row vector. And then when I applied a conjugate, it became A asterisk, B asterisk. But if A and B are real, then their conjugate will also be same. Now we'll talk about operators. So there are operators. The operators can also be represented using the matrix. So for example, the X operator, which was changing the bit, like 0 was becoming 1, 1 was becoming 0, that is represented using this 0, 1, 1, 0. Now suppose I want to apply this X on ket 0. So I will do simple matrix multiplication and I will get 0, 1, which is ket 1. So it means it proves that X is working in the way I wanted. So it was basically flipping 0 to 1. So here also you can see that I started with 0, I applied a X and I got a 1. Another way is that I can also get a adjoint of the operator. So again, same, take a transpose, and after transpose, we can do a complex conjugate. But since they are real numbers, 0 and 1, their complex conjugate will also be 0 and 1. So you can see that after making the adjoint, it is still x only. Now we'll multiply x and x adjoint, and you can see that ultimately, finally, it becomes identity operator. Identity operator, if it applies on ket 0, it will remain ket 0. If it applies on ket 1, it will remain ket 1. Now from this mathematics, it's simple matrix multiplications. I can conclude three things. One, that there are some operator, for them the adjoint is equal to them. They are called Hermitian operator. And then there are some operator whose multiplication with their adjoint gives identity operator. So they are called unitary operator. So I'll be using this concept, that's why I explained it. And since A adjoint is equal to A, I can also say A square equal to I. Now we'll talk about blind quantum computing. So in blind quantum computing, why do we need it? So the thing is that a client usually have not a quantum computer, at least not now. So what we do is we have different computers like IBM quantum computer, where we send our operations to perform. So we send our input, we tell them what operation to perform, they do it, they return, and we see the result. Now, all this is fine, but what about privacy? So if I invent an algorithm, I send it to them, they will know what is the input, what are the operations that I am performing. In fact, they will know my entire algorithm input output. So my goal is that can I somehow hide my input, my operations? So that is blind quantum computing. So my intention is that I have some input, I want to run some function on that. So for that, what will I do is, first I will mask my input. Then I will send it to the our quantum computer and let it do the operation on that. Once I get back this operation, somehow from this fx dash, I have to get my original fx. This is my goal. So in this way, I can get from x, I can get the fx. Now, it's important that from x dash, I cannot get back x. That's not possible. Otherwise, even the quantum computer can get back my original input by applying that function. So this is our problem statement, that there is a client who has less capability. They don't have a universal capability of a quantum computer. So they will send their input to a server, and somehow we have to hide the state, input state, and the quantum operation. So let us start with how can I mask my input. So for masking my input, what can I do is I can randomly mask my input using one of the poly operator where x, y, z. So I can mask like this. So I can suppose in this example, I am showing that I will use x gate, x operator. So I will apply the x operator on 0 based on some random flip of coin. So sometime I'll apply, sometime I will not apply. Okay. Now, in this way, I have hidden my input, my original input, because the server doesn't know whether this time the input was flipped or not. So they cannot exactly guess my original input. So in that way, for server, my input is hidden. Done. Now, my question, so next part is that somehow I hid my input, but I should also get back my operation, the original operation that I wanted. So it means that my input is suppose ket psi, and I want this operation C into ket psi. I want this somehow. Now, if I mask it, I will use some operator like sigma up, and then I will ask server to do some operation. Somehow I should get back my C hash, C ket psi. Now, server operation can be different operation. Okay, so we'll start with first operation, which is called Clifford operation. Now, what are Clifford operations? So Clifford operators are basically unitary operators. They transform one one poly operator from one poly operator to another poly operator, and we say like this, that this sigma is conjugated by C. C is the Clifford operation. Now, since it is unitary, we already saw in the last slide that C adjoint C or C into C adjoint should be identity. So that is fixed. Now, my masked input was sigma into ket psi. I sent it to server. Server applied a C, which was the Clifford operation. Now, somehow I have to get C into ket psi. So how do I remove this sigma? So for removing this sigma, what I can do is I can apply this transformation. C, sigma, and C dagger. I will apply this. Now let me apply this. So what will happen is that once I apply, you can see here in the middle, there is a C adjoint into C. So C adjoint into C, it will become identity. And then I am left with C into sigma into ket psi. Now there are two sigma square. Again, sigma square will become I. You can see at that side on the top right corner. A square will become identity. So A square is also left. Sigma square is also gone. So finally, I'm only left with my operation, that is Clifford C operation into the ket psi. So this was when the server operation is a Clifford operation. Now we'll consider another case where the server operation is not a Clifford operation. In that case, I will take a specific example of this phase operator T. So after my server operation, it will become T into sigma ket psi. Now in this operation, there are two possibilities, that either my T operator commutes with sigma or it doesn't commute. Okay. So now in quantum computer, what happens that the order of applying the operator matters. It's not like sigma T is equal to T sigma. So order matters. So first I will assume that commutation is allowed. Second time I will assume that commutation is not allowed. So if commutation is allowed, it means I can write T sigma equal to sigma T. Fine. So in that case, I will only use, for unmasking, I will use sigma. So sigma dash equal to sigma. So I will apply this on the after the server operation. I will commute it. So T sigma will become sigma T. And now there are two sigma, which becomes sigma square, and sigma square is identity, so gone. So I'm only left with T psi, ket psi. So done. So this time I achieved what I wanted, only the operation multiplied by my input. Another case will be when the commutation doesn't work. Now, if commutation doesn't work, then what client will do is, client will, whatever input it got from the server, that T sigma psi, it will again apply sigma on that. Same sigma it will apply. So now it will become sigma T sigma ket psi. Done. Now after that, it will ask server to apply another gate is there, S gate. S gate is basically S equal to T square. Means it has 2T. So when server applies this 2T, it will become like this. S sigma T sigma ket psi equal to S, I simply replaced with 2T. So it becomes T sigma and ket psi. Now can you see in the middle, T sigma is repeated. Again, I can say T sigma square, and T sigma square will become identity. So I'm only left with finally A T psi. A I can remove because this is just an amplitude which doesn't affect the quantum properties. So I am finally left with only T ket psi. So I proved that the server operation is either a Clifford operation or non-Clifford operation. And in non-Clifford also, either it can commute or not commute. In all the cases, I am getting my final output. But there is one question, that whenever it doesn't commute, I have to ask server to apply S gate. Now server will know, array, it is not commuting, that's why he sent me. And if it is not commuting, it means that it's a T gate, or the sigma has X or Z. So if it knows, sorry, it contains X or Y. So if it knows, then blindness is not there. So what we can do is, irrespective of whether it commutes or not, every time I will ask it to apply S gate on the input. And when it commutes, only thing is I will send it a dummy qubit to apply the S gate. So sometime I require it to apply S gate, another time I will send it a dummy that apply on this dummy qubit. Server will not know. He will only know that I have to apply first operation T and second operation S. Now we want to mask the operation, because we already said that server can apply C gate, T gate. So it means they know that what operation they have to apply. So I want to mask that also. Now there are a set of universal computation. So for example, we have H, C naught, T, S. So what I can do is, instead of saying that no, I only want to apply C or T or S, I will say that apply this entire set on my input. But whichever operation I don't want, suppose I don't want C naught, I don't want S, so for them, the input will be some dummy qubit. So whenever an operation which I do not require, for them I will send the dummy qubit, and whenever the operation I require, I will send the actual qubit. In that way, server knows that every time he is applying all the four. He doesn't know which one is dummy and which one is the actual one. So in that way, I can mask my operation. So to conclude, in this way, I was able to hide my input. I was able to hide my operations, and I was able to obtain my desired operation. But it doesn't guarantee data integrity. What if my server doesn't apply the gate that I'm asking? It may apply some other gate. So in that case, that will be a different topic. We'll meet another time for that. Thank you. That's all from my side. So, yes, please.
The point was basically the transformation of the input the client was doing. First thing is, does he need a quantum system to do it, or he doesn't require? That is the first question.
The basic operations which we used for masking our input, X, Y, Z, those are poly operators any basic quantum computer can do. Okay. Only for high level H, C naught, T, S, we are asking the server to do.
Okay. Now, in the last slide where you mentioned that 4 options are there, see the combinations, permutation and combination of whatever that is, a large quantum system can probably figure it out, right? If I say dummy qubit, because we are using only 4 choices, right?
So these 4 are universal
gates.
Universal gates. So it's like any
gates.
circuit can be formed using these 4. So what I have to do is, every time I will send this only, do this, do this. And if I really require some operation, I want H and T. So for them, I will send my actual qubit.
Okay.
For the operation that I don't need, C naught and ends, I will send dummy qubit. And their response, I will simply disregard.
Okay. Okay. My point was basically the server if a server wants to break it, meaning this kind of thing, so it can also try the multiple combinations. Is it possible? It can try to do the attack of it.
So as of now, we only discussed the server blindness.
Okay.
Okay. Now, second part was which I put in, but that there may be a possibility that server is not doing what I said. So how do I maintain my data integrity that, yes, whatever data I say, or it tampers the data? So that part is a separate research problem.
Okay. So one point is basically when you started the presentation, this was more or less looking like a crypto hashing algorithm.
Okay.
Because anyway, you said that this does not guarantee the integrity of the data. Because the reverse operation is not possible, right, in any possibility. So that is what actually was mentioned here also in your representation in the beginning.
No, reverse operation is possible. So for
No,
example,
f of x.
if I
back
do a
to-
not operation, again, if I apply the not operation, I will get back my original input. But server doesn't know that whether I applied the not or not.
Okay, fine. Okay, then that's the point I was making.
So that was x raised to the power r, where r was random bit, 0 or 1. If r is 0, I will not apply x. If r is 1, I will apply x. But server doesn't know.
Okay, yeah, that's
Okay, thank you. Any other question? Okay, so that ends the session for today. So I will request Dr. Satyanarayan to present a memento to our session chair, Sri Ramchandran.